Hello, everyone. My name is Luis, and I'm a software development director at Oracle, and I lead the replication team. I've been doing MySQL replication for 12 years now. And today I'll be talking about MySQL replication performance, efficiency, and the cloud. This is a work that has been, this presentation is a work that has been done, well, a lot of work has been done with Vitor Oliveira. So his name is also on this front slide because I want to give credits to him as well, right? So going through this presentation, I will begin by setting some expectations. This presentation will show some of the technical aspects of MySQL replication and then reason about the impact of latency and other things in MySQL replication performance. This will be kind of an interesting session because it's different from the usual. We will do some thought experiment here, so keep your minds open. So the agenda is not very long. I'll start by introducing the subject at hand. Then, after motivating the subject that I want to discuss, I will introduce a model that tries to capture and abstract the performance characteristics of MySQL replication, and then do some analysis over the the exercising of this model, and then conclude this session. So, some quick notes about benchmarks. Benchmarks are often expensive because they often involve a lot of resources in terms of compute and even people. Good performance architects are hard to come by, and good performance architects that look at the, that know the product inside out, that are able to dig into the bottlenecks and the details of performance analysis are very hard to find. So there's a lot of resources usually involved in benchmarks. Benchmarks are also can also be very time consuming, mostly because they are in a highly iterative process. Often we find ourselves doing, run the benchmark, analyze, figure out what's going on, exercise some judgment, and then maybe we find that something is not exactly as we expected, and then we repeat the whole sequence again. And this is, in some cases, very noise sensitive or even error prone. On the other hand, benchmarks are quite useful. We can use them to do performance regression testing, find bottlenecks, fix those bottlenecks. We can use them to do capacity planning, anticipate behavior by testing the system that we want to test in out of the ordinary situations like peak loads and so on. And we can also rely on benchmarks to maximize the efficiency of the overall system deployed by doing all of the things that I've mentioned earlier. And benchmarks, we can use synthetic workloads, or we can even use real workloads or real traces of our workload to exercise the system in a controlled manner and figure out how is it going to behave. But benchmarks results alone are not sufficient. Sometimes we often find ourselves, engineers and developers, we often find ourselves in the need of asking why or how, why is this happening? How did this happen? How did this result happen? And what explains it? So we also find ourselves often finding the need to be able to predict, diagnose more accurately what's going on, extrapolate. Looking at the benchmarks results alone, they give us some data points, but we need to dig deeper often. And then there's expectations versus reality. We often test a piece of software that is deployed on top of many different components, and then these components interact between themselves, which creates fuzziness and provokes uncertainty in the whole thing. And then different components have different limits, often unknown, meaning that the engineer doing the benchmark might not even be aware of what these limits are, because he missed those, or even because he can't, because the component he's deploying on is just a black box. So the overall details of the system end up end up making a big difference when we reason about it. So I will just present a very simple benchmark here to use it as a starting or a baseline for the rest of the discussion. This benchmark is very simple. We'll be using 3 servers. In some cases, they will be deployed across different ADs in OCI. There's one client machine which is attached to the same, that is deployed in the same AD as the primary server. And then we will use the sysbench workload, which is a very popular workload within the MySQL ecosystem, to exercise these deployments. We will use 3 different mixes of the workload: OLTP read write, OLTP write only, and update index. And then we will use those shapes that are listed there. So just by running the benchmarks and comparing, for instance, one server versus one cluster with 3 servers deployed across ADs, one in each AD, and then comparing virtual machines versus bare metal servers, we can see some of the results that we observe in these charts. These are direct results from the benchmarks that were done. We can draw some conclusions from them. In some cases, one single server is outperforming a cluster, and in some other cases, a cluster is outperforming a single server. But the raw numbers fail to capture the reason why. They are just raw numbers. So in some cases, that's enough. But for performance engineers, we have to dig deeper usually. And then if we change some parameters, for instance, in this case, we change durability settings of MySQL, we can observe the system behave in a different way. And if you look at these charts, they will just tell you, if you reduce durability, so if you disable the piece of software that engages the storage subsystem often while deploying MySQL, you can see that by not doing fsyncs as often as you should, then you can see that replication or a cluster will exhibit a very big performance increase. And again, these are numbers, right? They don't exactly tell us why. They give us an indication of how the system behaved or change the behavior while doing this reconfiguration. So what exactly does this benchmark tell us? These results that I just showed, they represent a particular workload in a particular testing scenario. So there's always the need to dig further. What explains these results? Can I expect the same behavior for my workload in the same setup? And if I do a slightly different deployment or setup, how do these performance results compare between the 2 setups? And if I actually configure things slightly differently, and if I tune this thing here, and if I turn that knob there, what would I expect, and could I make the system more efficient itself? And also in the back of my mind are, did I miss something here? Were the measurements properly taken? Was the system fine-tuned as I thought it would have been? And then, the ultimate question is, what can I reliably estimate using these results? So these are questions that are natural, and they're not answered by just looking at the raw numbers from the benchmark. So can we actually estimate the behavior? Because benchmarks capture 3 different things, and these three different things are often hard to distinguish between themselves. They capture behavior of the software that we're actually trying to measure and assess. So, the implementation behavior of certain features exercised by a specific workload in a particular way. So it gives us a view of the software that we're trying to assess, how of the behavior of the software that we're trying to assess, exercised in a specific way. It also captures interference, noise, and limitations of the test bed. So there's often, as I said earlier in some slide, there's some fuzziness and uncertainty that is introduced in the system just because we deployed on top of different components, and they have their own behavior and their own interaction between themselves that can cause interference to what we are actually trying to measure. And then there's the computing infrastructure, which have architectural, properties and have their own configuration details. So all of this feeds back into these raw numbers that we capture in the benchmark. So at the end of the day, if we could actually model a representation of the system, then it would be helpful for us to calculate and understand how the system behaves when certain aspects are changed. So we could look at benchmarks and say, yeah, it makes sense that it behaves this way, because if I understand the underlying system, I know how it will potentially behave, and the surprise cases would be more, it would be less. So it would be more of a rare situation. So to build such a model, that abstracts the whole thing it's not an easy task. It's a complex thing. There's a lot of things working together and interacting, a lot of components, a lot of behavior that is not the sum of the individual components' behavior, but it's actually something that results of the interaction between all of these components. So it's a hard thing, but we can at least try to get a simplified abstraction that allows us to get a glimpse, an overview of how the system should behave. So this model can be built on information such as the architecture, so the specifics of MySQL and MySQL replication, and how it uses the computing resources. And then we can also look at the characteristics of the workload, like the number of queries, the size of the data set, and the size of the memory that this data set will consume. And we can look at the computing characteristics of the system that we're deploying on, like network latency, bandwidth, the number of processor cores, the number of network hops that our traffic needs to go through when doing replication or when doing client-side requests. So if we think of these different aspects, we can try to reason and build a simplified model that could guide us through the analysis of benchmark results. So let's try to start simple. Let's try to exercise and create such a model. So we need to think about, okay, so what are the replication phases in MySQL? What is the network access pattern for a simple transaction execution path? What is the impact of the time it takes to write things to storage and make sure that they are durable in storage? What is actually the access pattern to storage? And what are the particular phases of this execution pipeline that are stressed in the deployment deployment that we have done? And if we look at this model, we see that it's a lot of there's a lot of it that is influenced by latency. And the fact is that the main factor affecting performance of a MySQL deployment is latency. Latency impacts the connections between the client and the server and storage subsystem, the server and its replicas in a replication topology. And in addition, transaction execution is affected by how much time it takes to do the fsync of the redo and the bin log to disk. I'll go into the details of all of this when we go into the specifics of how the underlying system works. But the bottom line here is that latency is the major impacting factor for MySQL replication performance. And if we bring in cloud environments to this picture, we can think of clouds as some environments that are inherently distributed. There's a lot of different components interacting between themselves. So there's a lot of networking involved. And often these components are themselves highly available, which means they have their own type of replication subsystems. So this is a very network-centric kind of environment. And the network itself is used, consumed, and shared by all of these different components and even the different tenants like customers and so on. So all challenges come into the picture again because storage has been has been getting faster and faster. But when we talk about network storage, then again, we need to pay some latency to access the actual network, the actual storage through the network. And then computing power is built. So we need to make sure that we use the resources in a reasonable, in a sensible way, so that we don't get, large bills just because we fail to do the proper capacity planning. And this is also something that we need to consider in our models. And again, network bandwidth may be limited since it's a shared resource between virtual machines, between the different components in the system, between client applications and so on. It also impacts latency at the end of the day because it can be overused. So if we open the hood and we look at in the inside, we can look at this pipeline of the transaction execution in MySQL. So there's the first phase, which means that the server receives a request from the client. It executes the request. Let's say that the request is the transaction. So the server receives the transaction, executes the transaction, spends some time going to storage to read the data from storage, spends some time writing to storage to write the redo log, and spend some time writing to the binary log, and then fsync this thing. Now at this point, we are taking all this latency and then spending latency in the fsync. We're spending latency on accessing the storage and so on. So once we are done by preparing, because we have to run a two-phase commit between the storage and the bin log, and that's the first fsync. So when we're done with the prepare phase, we write to the bin log, again, more storage involved, and then we fsync again, and we eventually send this out to the replica. So all these phases we can think of, okay, there's some abstractions here that we can consider and apply in our model. If we bring in group replication, which is another replication technology for MySQL, we can see that the pipeline is more or less the same, except requests or transactions are intercepted before they are actually written to the bin log. So the fact is that this contributes with more additional latency to the overall pipeline of the transaction execution. And if we configure group replication to be synchronous, with this parameter consistency after to do synchronous writes, then it means that once we replicate to the group, we will wait for all of the reminders of the servers in the group to acknowledge back, and this again contributes to the overall latency of the system. So this is also something that we could potentially capture in our model. So keeping this in mind, we can build this model where we materialize it. We can build this model and then materialize it in a spreadsheet. And try to correlate all these abstractions that we can think of doing in the system. So like there's client server latency that we can abstract, there's transaction execution time, there's data read time, read and write and sync to the database engine log. There's group replication time that we spend propagating the changes, transaction changes through group replication. There's time we spend writing to the bin log, and then there's also syncing time of the bin log. But in addition to this, there's also abstractions that relate to the system on which we deploy, like the number of cores, like the interference between client threads when we have lots of different threads connecting to the system, lots of different client connections in the system. And then we have properties of the workload itself, like the number of queries per transaction and so on and so forth. So if we materialize this model in our simulating in a spreadsheet with all these correlations, we can try to do this thought experiment. And this is what we'll try to do here in this session. But how if I tweak this knob, if I change this variable here of the system, how will it react? What's the expectation of the system reaction behavior when I do these things? So what comes next in the next slides are just experiments, like exercising this simulator and considering the underlying properties of MySQL replication captured in this model. How do we expect the system to behave? These are not actual measurements. These are not real values, real benchmarks that are telling us anything about how the system behaves with real workloads. It's just a thought experiment to see what's the delta when we change these variables along the way. So if I look at the system and I exercise the simulator and think, okay, what if my transactions get more complex and the number of queries per transaction increases? How would my system behave in that case? How would it evolve over in such scenario, right? So this is exactly exercising the simulator is telling us here, right? So we are looking at OLTP read-write, OLTP write-only, and update index. And we're saying, okay, read-write every transaction takes a second. There's 20 queries, 20 statements in the transaction versus the rest of the other types of workloads. So if I make these queries small, if I make this transaction smaller, as in OLTP write-only or update index, the system will behave in a specific way as depicted here. Again, this is all thought experiments. So at the end of the day, we all know that our workload specifics drive the results of the benchmarks, but how does the system behave as we vary the number of clients and the transaction mix? It's an interesting observation. And what happens if I change the number of cores available for me to run this workload through the system? So then we can see that as the number of concurrent client connections in the system grows, for the same workload, we can see that the gain from going to larger machines becomes smaller if the effort per transaction is low. And then we can see also that at low thread count, the benefit of many cores is not as appealing as it could have been, as it could have been perceived, right? So this is nothing. This is obvious, but it's interesting that we can capture the behavior of the system in this simulator. And what if I locate or place my clients away from the server, right? So how will the system behave? And this means that for a workload that has large transactions with 20 or plus statements, we can observe that it actually takes some large impact. because the customer application will be paying the price, the latency price to connect per state, not to connect, but to interact with the remote server on a per statement basis, and then and then it shows on this curve here. And what if I change my storage technology? What if I get faster storage or slower storage? How will that impact the overall behavior of my MySQL replication setup? And as we can see here, we have some well, the performance of the storage is important for the MySQL performance. Ultimately, that's also obvious, but while the throughput can grow to the point where the difference is less visible at lower thread count, we already start seeing some considerable impact by just looking at the output of this simulator. And then, okay, so I mentioned earlier that in some of the charts that I showed earlier in this session, that okay, if we relax durability, what's the impact of this in the overall throughput of the system? And if we make it so that we don't fsync per transaction commit or per commit, we can see that the impact for lower thread counts is you also already start seeing a big performance impact. Of course, this depends as well whether your storage whether your storage latency is large, right? If the fsync takes longer, then the impact is bigger than if your fsync is smaller. But this is captured in this model as well. What if I add group replication to this mix, right? How will the system behave? And we can see that if we add group replication to the system, so we build a cluster and we have 3 servers and so on replicating, we can see that it has an impact, right? Replication itself in group replication will have an impact in this because it will contribute with additional latency. If we reduce or relax the durability, then we can see that we can make group replication almost be comparable or in the same line as the single server. This is in the model, right? So this is what the model is trying to convey. And what happens if in group replication, so in the cluster, we increase the distance between the different members that are part of the cluster? So it has impacts. If we place them very far away, we start to see that the system, we expect the system to behave in such a way that the throughput will be impacted considerably as latency grows. And what if we have group replication running and we connect our clients locally to the server? So they are deployed very close to one of the servers. And what happens if we take the client application and we put it remotely? This is very similar to the behavior that I mentioned earlier when, if I have a client application that is accessing the remote server and I need to pay the latency per statement in the transaction. An interesting case here, though, is if we connect the client closer to GR, we can to a GR server, we can pay a minimal latency penalty per transaction, per statement, and then we can pay only the network round trip latency at the commit because of the algorithm, replication algorithm for GR. So at the end of the transaction. And what happens if we add to the mix, so to this infrastructure, a MySQL router? So it means that we add a network hop between the client application and the server. This, in fact, actually contributes with additional latency, and it becomes, in a way, similar to keeping a client application away from the away from the away from the well, further away from the server itself. So these are all impacts on the client side. But if we look inside the server, what exactly, if I had to this mix the bin log, what is the impact of the bin log? Because if we have replication, we'll have to turn on the bin log. It will bring in latency. So what exactly is the expected impact of the bin log for a specific workload model in this model? And as we can see here, we have a slight degradation of throughput with a bin log. If we disable the durability, so if we remove the fsync, we can see the system the system with a bin log tending to be closer to the system without the bin log in terms of throughput. And what is the impact of the buffer pool size in the overall throughput of my system? How will the throughput vary if I vary the size of the buffer pool, or if I need to access more often the database to bring in data that is not yet in memory? So yeah, on those conditions, we can see that the system can exhibit this kind of different in behavior according to this model. And with a small buffer pool, the effective use of the computing resources is impaired. This is also a bit an obvious statement, but this is what the model tries to capture here is, okay, if I change this over these values, how will the system behave accordingly? And one thing that is also interesting to understand is, okay, but if I bring all these, if I open all these client connections to the server, how will they interfere with themselves, and will this actually thrash the system instead of actually giving me this scalability that I was hoping for? And this model captures this context switching loss estimate, which is an abstraction that tries to capture this interference. And the context switching between threads is expensive. And as there are more threads in the system, there will be more context switches, and then the system will degrade and behave a little bit like is exposed here. So, to conclude, benchmarks are a good tool to identify bottlenecks, optimize setups, or simply validate deployment designs. But results alone are not enough to understand how the system behaves when we change certain aspects of it. So they're not enough to reason what is going on behind the scenes. Just by looking at the bare numbers, there's not so much you can take out of it, unless other than the fact that the system behaves like this on this particular workload under this particular setup. And to understand how the system evolves over time when the conditions are changed, we need to understand the inner works of the system on the test, right? And MySQL replication, of course, is no exception to this rule. And at the same time, when we think about replication and coordination between servers and so on and so forth, this has a lot to do with networking and latency. And when we think about cloud infrastructures, we have to deal with the network and latency, and we need to understand how the underlying system is architected, whether it's the system, whether we're referring to the system that we're deploying on, or whether we're referring to the software that we're actually benchmarking, to understand how do these extremely distributed environments impact the system that we're trying to assess. And what we tried to do here was try to, do some thought experiment where we could look at MySQL replication, look at how it is architected, and think of a model, an abstraction that we could that could help us reason when we do performance benchmarks of how the system should behave and whether do we have an outlier here, is this a surprise, and if it is a surprise, why is it so, and so on and so forth. So thank you. So it's time for questions and answers, and lucky of us, we have Vitor also here. He has been looking at the questions, and he has questions of his own as well. So Vitor, can you shoot a few questions?
Hi, thank you, Luis. I have a few. So regarding the impact of the workload, the round trip time between the client and the server seem to dominate the execution time of the transaction when the latency of the network is high. So this seems to suggest that not only we need to look at the computing, so the query, but we also need to look at how we distribute the query between the client and the server. So using things like stored procedures may be a good approach to just try to diminish the impact of the latency. And what do you think of that?
Right. Yeah, I tend to agree. Yes. If your server is far away and you want to minimize the round trips within a single transaction, maybe your transaction has, like I said, 20 statements in it, then you could push some of the execution logic to the server side and reduce the number of interactions with the server per transaction. You could also try to minimize the number of statements in the transaction itself to avoid the several round trips per client during the transaction execution to the server. Does that make sense?
Yes. And it's also something that's regarding, for instance, on the side of GR. Even if we look at the part where we have a GR server that we put closer to a client instead of putting the server in a faraway data center with all the nodes connected. This also seems something that can be explored so that we can reduce the total latency of the transaction, right?
Right. Right. Yeah, so I tried to make that point during the session, which is if we look at the inner works of how replication works, we can understand that there are certain things that we can already optimize and then capture in our model and then reason about those, like the fact that if you co-locate one client together with a GR server, you pay very small round trips to that server, and the way the replication algorithm works is that you execute things, you execute the transaction in the pipeline I showed, and at commit time you say, okay, now I'm ready to replicate and propagate this to all the other servers in the system. So what this means is that instead of paying the latency n times once per statement, in the case your client application was far away, you pay the latency once at the end of the transaction. And this is actually an interesting setup for those that try to explore this aspect of group replication.
Okay, thank you. And also you mentioned that using network durability. So basically replacing the durability that we have on a single server, where we must make sure that we don't lose transactions, and we replace this. Can you explore that a bit further?
Yes. So network durability within this context, it means that if we disable the local fsinks to storage, we can rely on replication to guarantee that the changes will survive in case of a failure of a single server. If that is a trade-off that your setup can deal with, then that may be a way to increase the overall system throughput. So at the end of the day, we're just basically delegating the durability to the replicas, right? So if one of the servers fails, the replica will still get the changes, and this is possible in the case of GR because we replicate and synchronize all of these different replicas before the actual commit takes place. So the data loss doesn't come into play in case we have a single server failure.
Yeah. Okay. Thank you. One last question. You showed on one of the slides that transaction consistency equals after, and you mentioned that that makes the apply and GR synchronous. What does that mean exactly?
Yeah, so that basically means that it's the previous question was a good segue to this, because it basically means that when we do this replication in group, when we replicate the transaction in group replication, it means that the originating server will wait and collect acknowledgements from all the other servers. And these acknowledgements, in addition to just the replication parts, these acknowledgements will just convey the information that this transaction has been applied everywhere already. So it's effectively replicated and applied everywhere by the time we reply to the application saying that the transaction has committed.
Okay. Thank you. I have no more questions. So back to you.
Thank you. Thank you, Vitor.